So hello everybody. I hope you can hear me. Bill, is that okay? So thanks very much, Dominique, for the nice introduction. And thanks everybody for being in the room to listen to me. And I hope that what I have to say will be of any interest for you. I can tell you it's a difficult job to prepare such a lecture. It's been worrying me a lot. So if it's not up to what you expect, I'm sorry. But the thing is that it's very difficult because you have to make things simple enough for the non-specialist, but you still keep some interest for people who know more. So this is why it's a challenge, and I really try to do my best. Okay, so let's get moving if I manage to use this computer. Yes, a laser pointer, great. Okay, so I'm going to talk to you about geochemistry in the inner Earth. And so what I want to do is kind of go through, what happened on the Earth since it was formed 4.5 billion years ago. I think this is an artistic vision of how the Earth looked then on the left-hand side of the slide, and how we went from there to the situation today, where we have here a real picture taken from space of the Earth, with water, continents, and so on. Things changed a lot, and I want to try to evaluate how much all these changes impacted the composition of the interior of the Earth. So I'm going to go through a timeline to start with. So at the beginning of the Earth, during the Hadean, several very important processes occurred. The core was formed, metal core. There was some heavy bombardment at the surface of the planet, and there was most probably formation of a magma ocean in the interior of the Earth. So on the top of the slide here, you see the timeline, and we are located at the beginning here between 4.5 and 4 billion years. The heavy bombardment had certainly some impacts about probably maybe ejecting some material out of the planet to maybe form the moon, and changing the overall composition of the leftover Earth. Importantly, during core formation, an important consequence is the fractionation of various elements. So siderophore element went into the core, while lithophile elements went into the mantle, and creating significant changes in trace element ratios. During the Hadean as well, the magma ocean shown here, it's a figure from Labrosse from 2007. The magma ocean crystallized, and so that also has probably some important implication, because it could most probably created layers in the inside of the mantle. So that's things that you should keep in mind when later on in my talk. During the Archean, so starting from about 4 billion years up to roughly 2.5 billion years, at some time during that period, continental crust was formed. So we see here on the right-hand side a schematic figure done by Bruno Duim in 2017. I think it's a very nice figure, where it shows the proportion. On the y-axis, we have the volume of continental crust. So 100% means the volume of continental crust today, okay? And 0% means there was absolutely no continental crust compared to the 100% of today. So if we start at the beginning of Earth's history, there is nothing. And you can see that all these lines correspond to different models that have been suggested and published about the proportion of crust, of the present-day crust volume that was existing at that time in the past. So you see that between 4 and 2.5 billion years, you know, the estimation of how much crust existed is extremely variable. Some models have even more than 100% of present volume, and other models have basically hardly anything, okay? So there is a lot of unknown there. And the question is also, then the other question is, when did it start? There is a big debate about that. When was the first continental crust formed? And you see in all these curves that it can, for some people, it's as early as a very early Earth in the Aegean, but a lot of other models suggest that the crust started forming much later during the Archean. So in terms of geochemistry, formation of the continental crust has some major impact because by creating a felsic crust, we create a reservoir that's enriched in trace elements. And the consequence of creating such a reservoir is that you create a depleted mantle, a mantle that's depleted in the equivalent trace elements. So that has implications for the long-term evolution of the mantle. And then, since the Archean, so since 2.5 billion years ago, the beginning of Proterozoics, all the way to today, basically the very important thing was plate tectonic. We're very sure of the existence of plate tectonic recently. When it started exactly, it's also a matter of debate, but there's been very consistent and long-term plate tectonic recognized by looking at the geology of continents. So what happened with plate tectonics is that basically some material that was at some stage present at the surface of the Earth is sent back to the interior of the Earth in subduction zones. So it can be continental material, it can be material deposited in the ocean on top of the oceanic crust. So this material, this sedimentary material, will have a composition more or less equivalent to its source, but it can be modified, as we all know. And it can be the basaltic part of the oceanic crust, which is also sent back into the mantle. So also, because of plate tectonic, such material can be re-injected into the mantle. So the consequence in terms of geochemistry are that we inject felsic and mafic material enriched in trace element relative to the depleted mantle, and we inject that into the depleted periodic mantle. So it's going to have consequences in terms of its absolute concentration, but also it has potential of creating heterogeneities. So the question I'm going to address during the talk is how all these events are affecting the Earth's mantle, and what can we detect? So can we detect an impact of plate tectonics? Can we see that in the present-day mantle record? And do we have traces of the early differentiation of the planet? Can we still find some markers showing us that's what happened in the early Earth? And to do that, today I'm going to focus on present-day mantle plumes. So this is the present situation where we sample mantle by plumes. On the left side, here, is a very nice figure from French and Romanovich, published in 2015, where they show that volcano that occur at the surface of the ocean here in the Pacific actually have their origin into some kind of roots that can go pretty deep down into the mantle. Here, actually, on this figure, it stops at about 1,000 kilometer depth, but in some of the other figures of the paper, it goes further down. And so it can be demonstrated, for example, like for Hawaii, it is very likely, and here is Hawaii on the right side, a figure from Cortillo. It seems to be that the root of the plume occurring in Hawaii might be going all the way down to the core mantle boundary. For other plume ocean island basalts, the situation is maybe less clear and we're not sure of where it comes from, but it just comes from deep in any case. So it samples the deep mantle. And so that's what we're going to focus on all this mantle plume volcanics. Before going into there, I just want to make a reminder for the young people who basically started doing geochemistry a few years ago. Metal geochemistry, I would say, did start when about 45 years ago. That's what is shown in these very old figures drawn by hand, as we were doing in these old days, not on computers. And that's when the neodymium isotope measurements were developed for basically for lunar purposes, studying lunar samples, but then it was applied to the interior of the Earth and to mantle rocks. And so in those days, so I'm talking here about the late 70s, beginning of the 80s, mental geochemistry and life was very simple. There was, as you can see on the left figure, there was about a maximum of 10 samples that were analyzed, very easy to plot by hand, you can see. For some miraculous reason, they define a beautiful straight line, a beautiful correlation, and this correlation has been called the mantle array. I think we still talk about the mantle array, and it was defined this way in the late 70s. A little later, here's a figure from a paper in the early 80s from Allègre, where we see schematically, there is no data here, but it's a model where you see the same correlation. And for the young people who probably don't realize that either, I want to point out that this correlation has been used to determine the strontium isotopic composition of primitive Earth. So the way it's been done is that the epsilon neodymium value of chondrite was known from neodymium isotopes, and the correlation here was used to go and determine the planetary value for strontium at 7045, and because we didn't know it, and it was determined this way. And when you see how now we change our opinion about how we explain the mantle array, maybe we should revisit this issue, okay? In these days, the interpretation was that the mantle was depleted as sampled by mid-ocean ridge basalts at the top here, and ocean island basalts, shown by here this box, were resulting of a mixture of primitive mantle here at 0 neodymium and 7045 for strontium, and depleted mantle. That's what's written at the bottom. So life was very simple. There was depleted mantle, primitive mantle, nothing else, and it was simple. 45 years later, this is what we have. This is a figure that you can find in in a review paper that Dominique Weiss led with another, is that 10 women? Is that correct? We are 11 women altogether. And it's a review of what plume component can tell us about the Earth. I welcome, if you can't access the paper, just send us an email and we'll give it to you. But it's a great summary, and we see here the results of 40 years of analysis. You should realize that there are thousands of data points that we compiled from the database PetDB and GeoRock, mainly GeoRock actually, and if database such as GeoRock didn't exist, this paper basically would not exist, I think, because it's impossible to do it by hand now. It's too much work. But anyway, here is what has been measured now on all the oceanic basalts. Thousands of points, and we see that the general correlation kind of still exists, but there is a lot of noise. Now we have a lot of noise. And what we need to do is explain how all this noise is created. So I'm going to just go quickly through the mantle zoo. So the people who know quite a bit about geochemistry of the mantle already know all of that, but I thought I should show it for the other people who don't know much about the mantle. So anyway, so the mantle zoo is basically the way, the diversity of composition has been characterized with a number of acronyms. So the first acronym is called DMM, which is a depleted mantle, and it sits at the top here. It's depleted. So here in this space, we have neodymium on the y-axis and strontium on the y-axis, on the x-axis. So this is depleted mantle. So the depleted mantle is also has low lead isotopic composition. Here are 2 lead isotopic ratios, and it has high hafnium isotopes together with high neodymium isotopes. The second part of the mantle zoo is the 2 enriched component, enriched mantle EM, 1 and 2, which are both enriched, and they're shown here with the greenish and the bluish color. So it's enriched because it has high strontium isotopes. That's basically the explanation for the name. So you can see them here in the various isotopic spaces, blue and green. Then we have the high mu, the strange one, which I will come back about a bit later also, shown here in orange and brown, which is basically high lead isotopic composition. And then we have in the middle, where you have all this concentration of points, we have what is called prima or sometimes FOSO, which is basically where there is a high density of data. And you can see the density of data from the curve here on the top or on the side, which shows the density of data located on each of the axes. Okay, so now how, what is specific to each of these components? So the enriched mantle number 2, shown here in blue and in blue here, basically there is a clear continental contribution. Everybody agrees on that, I think. And here are two figures to show that basically these rocks, the blue one here, have high strontium isotope like characteristics of crustal material and sedimentary material. And when you look at the nice work that was done by Bill White a long time ago, you can see that for samples from the Society Islands, one of the canonical ratio, which I'm not going to get into, is a ratio that's supposed to be constant in the mantle, is going down when the strontium goes up, which shows a mixture with some crustal material. This is the same islands. This is several years later and another canonical ratio, but we see exactly the same thing. When the strontium goes up, the cerium length ratio goes down towards crustal value. So this is one a clear evidence of the involvement of some material of crustal origin. Much better example for EM2, this is a paper published by Jackson in 2007 for the Samoa Islands, where it's absolutely obvious that there is crustal material because the strontium is so high that you can never find that in any other setting than old continental crust. And again here, it correlates with the lower cerium lead and correlates with lower niobium concentrations. So that's a very clear contribution. Now, something that I would like to show is that, I told you there was two types of enriched mantle, 1 and 2. The 2 is clearly crustal involvement of some crustal material. But I want to point out here in these two figures that when you look at the other enriched component, they have similarity in terms of trace element ratio. You see here that the EM1 type of rock is shown as Pitcairn, the purple circles here, and it's just like the EM2 society samples. When the strontium goes up, the cerium lead goes down. When the strontium goes up, niobium anomaly increased going towards continental crust. So it's very common features. But something important that was discovered not so long ago, that was about 2016, this component, which is here shown in green, the EM1 component, was at the surface more than 2.5 billion years ago. So now we have a bit of an age, because we knew that there was some crustal material in the source of this lava, but we have no clue of the age of the material. So this information has been provided by a stable isotopic system, which is called sulfur isotopes, and there is a measure of a deviation of the 33 sulfur compared to the behavior of the other sulfur isotopes, quantified as this cap 33 sulfur. And so what was shown here beautifully by Farkas in 2007 is that from today's situation all the way back to the great oxidation event, the sulfur isotopes had shown no anomaly. But anything that was older, between 2.5 and 4 billion years, had a gigantic anomaly. So now, when we measure sulfur isotopes within minerals present in the Pitcairn sample from EM1 volcano, we find, shown here in red, we find a negative anomaly. So that demonstrates that material that had suffered mass-independent fractionation more than 2.45 billion years ago is present in the source of this volcano. So what can it be? It's most probably because the anomaly, the sulfur anomaly, it shows that the material was present at the surface. So it's probably of sedimentary nature. Okay, so now we have a bit of dating on these enriched materials. And now let's move to the high mu type of composition. So I'll just remind you that this is the, whoops, I'm losing thing. This is the rocks with a very high lead isotopic composition, very radiogenic. And so I think there is quite a general agreement that To obtain this kind of value, you need to have a material that has lost a lot of lead relative to thorium and uranium, and a long time ago. Otherwise, you cannot have such a highly radiogenic composition. And how can you do that? I myself suggested a while ago, a long time ago actually, that this material was in fact basaltic crust that had lost parts of its lead long time ago and was sent back into the mantle. So this is a tracer, or its sampling, demonstrating that oceanic crust has been sent back into the mantle and can be sampled again. We quantified that more or less in terms of lead isotopes, and we see that it has to be at least 1.5 billion years old, the material, this recycled material. This is also consistent with the very nice work published by Jackson's group in 2013 on sulfur isotopes on some islands that have the high mu characteristics, and maybe it's too small for you to see here, but these are the green dots here in the figure, and here again, these negative values, and demonstrate that the material was present at the surface of the Earth more than 2.45 billion years ago. Okay. So another and important evidence, which is a paper that I published in 2008. It's a relationship between neodymium and hafnium in terms of isotopes. Here you see the field that defined by all the data that exist in literature. And here are lines that, that calculate the evolution of the present-day position of an old oceanic crust if it was created 4 billion years ago, 3 billion years ago, 2, and so on. It should lie on this line. If you take sedimentary material and formed 4 billion years ago, it should be down there and along this line depending on its age. What we see is that the trend defined by the data does not follow neither the oceanic crust lane or the sedimentary lane. What it shows is that you need to have both. You need to have a mixture of the two. You cannot have explain the trend of neodymium hafnium by having only recycled oceanic crust. You need to have a mixture of the two. So that's an important factor. So, what we can say is that there is recycled crustal material that creates mantle heterogeneity, and that's clearly the impact of plate tectonics. Okay, so now do we have constraints for what happened during the Aegean? And we have some, and they come from what is called the extinct radioactive systems, and there are two of them that probably most of you have heard about. There is this two short-lived radioactive system that existed at the beginning of Earth's history and do not exist anymore. The decay is finished. So the first one is the 182 hafnium that decays in 182 tungsten. We have the specialist of 182 tungstens probably in the room here. I can't see him. But the half-life is about 9 million years. So, and we have a second one, which is also very important. It's an isotope of samarium that decays into an isotope of neodymium. That's number 142. The half-life is longer, but it's still very short. So if you look at the figure at the bottom, you see that here we have a time since beginning of Earth all the way to today. And here you have the parent isotope. So you can see that for normal radiogenic isotopic system, for example here rubidium strontium, We had 100% at the beginning, and it has barely changed. If you look at these two isotopic systems, shown here in orange and red, you see that it goes, the amount of parent isotope goes down drastically, and within less than 500 million years, there's nothing left. So if we have a trace of the decay of these parents, either 82 hafnium or 146 samarium, in the daughter isotopes, it means that it was done in the very early part of the year, of the Earth's history, because there's no way to do it afterwards. It's instinct. So one beautiful work that I wanted to show here has been done by Andy Mündler with the group in Maryland, and it was published, the last of the series. The last one was published in 2020, and this is the evidence of the measurements done on oceanic islands for tungsten isotopes. And what we see here, this is a gray field, is a value that basically everything normal on Earth should have. And at the surface, this is it's a zero value. And what we see is all the data here for oceanic island basalt that are all negative. So there is a clear trend to be that the oceanic island record something that is negative and not equal to zero. And he also demonstrated that this negative value seems to correlate with some other primordial signature, which is a helium isotopic composition. Anyway, so what is interpretation at this stage? It's not very clear, but there are basically two solutions. Either it's some Hadean material that's saved in there ever since the beginning of the Earth's history and is sampled today, or its potential interaction with the core during formation of the plume, and that means that the plume would come from the core mantle boundary. Okay? The second isotopic system, which is the other anomaly I wanted to talk about, is 142, and I would say that up to the compilation that we made last year, there was no clear evidence. Here in the figure, we show all the data that exists on oceanic island, and you see that there is a gray field correspond to the normal crustal value, and you see all the data points that basically overlap because the error bars are relatively large, because these are very difficult measurements, very difficult to do. So at that stage, there was no obvious 142 anomaly in ocean island basalt, and potentially some small positive one in some Réunion island sample. So they've been working on that issue with Claudine Israel, and I don't know, maybe some of you saw a talk on Monday, but now I think we can say we have measured some significantly positive anomaly in one ocean island, in one ocean volcano. And these measurements were done on a new submarine volcano that's located in the Comore archipelago, next to Mayotte. And here are the data. You see here the little blue field is a reproducibility on the international standard. We've been able to go down to an error of 3 ppm when the previous measurements were at 5 ppm. And because of that, we can now demonstrate that in this volcano, we have a positive anomaly at +3. Okay? So it's significantly different from 0. And that, therefore, has a very important implication because it requires the presence of a depleted Hadean material in the source of that volcano. So what's the source? The constraints, we can quantify things, but to quantify things with two important constraints. The first one is that the positive anomaly in 142 has a value of +3. And at the same time, the 143 neodymium isotopic composition that we also measured, and I didn't show here, is constant, and it's also about +3. So the two constraints has to be combined, and thus requires some kind of mixture of various components to explain the two at the same time. And so the final calculation is that we need about 30% of depleted ADN material in the source. 30%, that's a lot. And the other 70% is normal kind of mantle that includes a little bit of recycled sediment. This 30% depleted human material, so what is it? It's basically, we believe, it's the crystallized bridgmanite that was formed during magma crystallization when the magma ocean crystallized, okay, at the very beginning of the Earth. We think that's what it is. But if you want more detail, you can talk to Claudine. She's certainly in the room somewhere, or you can ask me questions later. Okay, so what do we have? We observe anomalies both for tungsten and neodymium isotopes, and this suggests that there is a significant presence of ADN material one way or another in the inner Earth. So that's, I think, a first-order information that's important. So now I can summarize quickly what I said. So the mantle is affected by recycled material. I hope I convinced you. And that's the impact of plate tectonics. If there were no plate tectonics, probably that would not have happened. We have a clear signal in radiogenic isotope, and there is a presence of Archean material detected by sulfur isotopes. The present-day mantle also contains remnants of ADN material, material formed at the beginning of the Earth, and because we can detect positive 142 neodymium anomalies, and we detect negative 182 tungsten anomalies. So now, of course, this is going to bring us to open all sorts of questions for the future, and I want to leave it maybe to, next generation to work on. So then the following question, I have a couple of questions like that, or suggestions. The first one is, I think it's an important question, is how much of that early depleted reservoir is there in the present mantle? We've been able to detect 30% in the source by just having better data. So maybe it's everywhere, but we simply cannot detect it. So we need to improve the analytical error. We need to improve our tools so that, to be able to go down to better precision and better constraint on the quantities. Second open question. Are these neodymium and tungsten anomaly connected? The problem now is that people don't work on the same samples. That's a serious issue. I think we've been several oldies around in the room saying, come on, work on the same sample. So I think here is I am again, please work on the same sample. We should analyze the same sample for major elements, trace elements, radiogenic isotopes, stable isotopes, and these anomalies. We don't do that enough. That's, I think, something important for the future, and we should pay more attention to it. And last question. Well, my movie is working. I'm very happy. So how does this ADN material relate to the recycled oceanic crust that I was talking about with this sedimentary cover? Are they connected? Are they in the same place? Are they in different places? And where are they stored? And I think that's a question that we'll probably be able to answer if we work more with seismologists, with geodynamics, and people from complementary field that can provide totally different constraints. But that's an important question. We need to know where it comes from. Okay, so I think I'm over. Thank you.
Oops. Questions for Catherine. If anybody has a question, go to the microphone.
Yes.
Please.
You need to go to
microphone, Hal.
Thank you for letting me ask a question. It was a grand sweep, Catherine, and I congratulate you to this.
Thank you.
I have a very specific question on the final part, and the number that you put on the 30% of depleted material early on, that must be significantly model dependent. In that it would seem to me that it would depend, among other things, on when that differentiation happened.
Yeah.
So, you know, because the isotopes evolved very rapidly at that time. Mm-hmm. So would you like to comment on that?
Yes, sure, I can comment on that. When we made the calculation and we come up with a number of 30%, it's using the relatively young age, the age of the big late bombardment, creating the moon. So that's the age we use. If you use anything older, the quantity is going to be, I think, let me just think straight, I think a little smaller, but not very much. It doesn't make an enormous difference. The key issue is the concentration, as you well know.
Another question for Catherine? Don't be shy. I'm going to ask one while you think about it. Where else are you going to go to look for anomalies?
I guess you'd have to double-check Reunion Island. That seems to make sense, considering that, and I don't know, I mean, originally I thought that maybe, you know, they find this anomaly in something that could be sampling some primitive material, but since we have no clue how this material might relate to recycled crustal material, it could be anywhere. So I don't know. I think we have to look, you know, open eyes, try things.
Hi, thanks for the great talk. I'm Jussi Heinonen from University of Helsinki and Åbo Academy. It was recently suggested that the LLSVPs could be remnants of Theia, the impactor in the mantle.
Yeah.
Would you have any idea if that argument could be tested geochemically?
I don't know how you test it because, you know, geochemistry doesn't know where it comes from. The location is given to us by our colleagues. We don't know where it is.
But I mean, could there be some kind of geochemical signature?
Some signature? I mean, if it depends on what you think that the LSVP consists of. You know, it's been suggested that it could be a pile of a great, oceanic crust graveyard. It's been called like that, which is basically an accumulation of recycled material. But other people can also been suggesting it could be residual from the early phases of the accretion. We don't know. I mean, I don't know. Oui?
I'm going to try to help. The 2 LSVP, if the model is correct, under the Pacific, the mantle plume connected to the LLSVP in the Pacific are Hawaiian pitcairn. In the other LLSVPs under Africa, you have Kerguelen and Tristan and Goff. They have different isotopic composition in radiogenic isotopes. I think that contradicts the hypothesis of the impact. That's my opinion, whatever it's worth. Yeah. Another question.
Yeah, maybe I can say a little more about that, because I can maybe at least, yeah, because I don't know. I think there's a lot of shortcuts done between the surface location of the volcano and the potential connection down at the bottom. I think that things are not as simple as that, and we should be more careful. Wow. Yes, yes.
Hi, thank you for the talk. I have a maybe...
Can you speak louder?
Sorry, thank you for the talk. I have a maybe, I can't tell if this is a really absurd question, but if we were to be able to go down into the mantle and pull up like a square meter of it, would it look like an igneous rock or a metamorphic rock? Since there's all this stuff mixing around in there, at what scale does it look one way or the other? Do we know? Have any sense?
What scale? At what scale it's heterogeneous? I think it's not easy to say. I think it can be very small. It's been demonstrated in some melt inclusions. Some people working on melt inclusions have been able to demonstrate that within the same rock you can have very different compositions. So it's probably a small scale, probably. And, you know, modelers have been also calculating mixing models in terms of the physics. And you can have things mixed up at a very intimate scale. But you can also keep some relatively bigger pieces isolated. So I think there's several scales, in fact. Oh, somebody else.
Okay, last question. Go ahead.
Thank you, Dr. Chauvel, for the great talk. So I do have a question about how do you think, or what do you think is the extension of this depleted mantle source in the Haiyan? Was mostly like localized effect or like a global effect? Because in the happening, we're not seeing any of these positive values in the Archean, early Archean, to support depleted mantle source. So maybe it was small enough to homogenize during the Archean, or any comment on that? Thank you.
Yeah, I don't know. I would prefer if, where is he? Where to answer, but Rich? No, Rich is not in the room, but it doesn't matter. I don't know, you know, I think I thought for a long time that the 182 anomalies that are seen now in the present day ocean islands, it's probably a clear case for interaction with the core. So showing that in fact it's not ADN material in a sense, it just comes from the core and it's interaction. I thought that made a lot of sense, but I know there are some counter argument that Rich has been mentioning. But now that, you know, we also have, you know, a neodymium anomaly, I doubt. And I think we need to check whether things are connected or not. It's very important. Is it present in the metal? It might eliminate the possibility of interaction with the core, or it might confirm it. And that's useful.
Well, thank you, everyone. I would draw one conclusion to this discussion and the questions and somewhat lack of answers, is that we have work to do, and we have work to do talking to each other, pushing the analytical companies to break the limits in terms of sensitivity and precision. And welcome to the club. We need more young people. So my thanks again to Catherine Chauvel for speaking today, and thanks to everyone for sticking around. Have a great afternoon, good lunch, and tomorrow there's one more day of Goldschmidt. Thank you.